Okay, so now we have Sebastian Ratzenböck on significance mode analysis for hierarchical structure. So I believe you're unmuted.
Yes.
Yes.
Perfect. Okay, this is the,
yes.
So this is the next slide, right? Okay. Okay, moving from redshifts to kiloparsecs, we'll move into the very local galaxy. And I'll talk about our clustering code significance mode analysis for extracting stellar populations from large-scale surveys. In this case, our large-scale survey is Gaia, which has really, really good positional measurements of stars. And since Gaia came out or the second data release came out, there has been kind of a hunt for finding these stellar structures in our Milky Way. And what I mean by stellar structures or stellar populations is essentially, so just a recap for all of you in star formation, it's essentially stars that have been born from the same molecular cloud. They essentially travel together, and they are probes for many things, such as structure formation and evolution of the galaxy, the chemical enrichment of the galaxy, and also we can study exoplanet formation and evolution. And also, importantly, the stellar initial mass function can be derived by having accurate measurements about these things. And these stellar clusters come in different shapes and sizes, most prominently probably globular clusters, which, if just from effect of cataloging them, is very, very simple. You can just point at them. Even in this image here, we already see some globular clusters. We have essentially a full catalog. Then, since Gaia came out, people have essentially jumped on finding open clusters, which live in the galactic disk, and now we are starting to find complete catalogs almost in the Gaia data of these open clusters. The real challenge is here on the right-hand side, where we don't see an apparent overdensity, and this is essentially where we want to introduce our clustering algorithm that is fine-tuned to these situations where we have only a slight overdensity over background. Identifying these stellar populations is quote-unquote easy because the feature space is quite low-dimensional and easy to interpret. We have 3 positional axes, and we also look into the kinematics of these stars, since we know that the stars that are born together move together. However, as you already see here, we are usually confined to the projection of these velocities. So we have projection effects in the velocities. We have huge data sets, millions to billions of stars due to Gaia. Actually, most of the stars no longer sit in these stellar populations, in these clusters, so we have over 95% background noise. And there's quite a wide variety of these cluster morphologies that have been popping up in the last few years that have been found with Gaia data, which makes it, for example, not so easy to just run a Gaussian mixture model on this. And we don't really have accurate simulations or forward models that can reproduce this today, or which can reproduce the Gaia data set with the clusters that we find. So what people usually do is they go to simple, going back to density-based clustering methods, and I'll quickly give you a recap of how this works, and then I'll show you what we do differently and how we find a better resolution. So in general, density-based clustering starts with a data set that comes from a true underlying data distribution, and then one motivation or one definition of clustering is that each point is associated with a mode in this underlying density, and how you can then cluster is essentially just follow the gradient, and then you essentially find all the points that end up at one point. One cluster definition. Another that's very useful is the cluster definition of level sets. So here you see now in 3D this density field, where the third dimension is the density, and then we can slice this density at each level, and everything that's above and is a connected component is a cluster. What's useful about this definition is that when we slide this density from infinity to negative infinity, we can essentially obtain this cluster tree, which encodes the entire cluster hierarchy, which is an additional information that you don't have in these mode seeking mechanisms. In reality, however, we have to estimate the density, and this is prone to errors and usually results in quite a noisy gradient and results in a huge overclustering of our space. So here are our 3 clusters. They have been split up into too many clusters, and what we want to find is a way to prune this cluster tree in order to find the true clusters again. So there have been proposed some strategies in order to prune this cluster tree. The easiest is just you look at this density difference, and if this is small enough, you just merge. Or if the clusters are very close together in the feature space that have been separated, you re-merge them. This is these distance-based methods. Or if something exists for a very long time and then at the end splits, you can re-merge this again, which is this relative excess of mass implemented in the HTB-scan algorithm that's very, very popular. However, as you increase the sample size, typically these strategies are not really adaptive enough to really find the underlying clusters in the data set. And that's where we want to come in. We want to kind of go back and think about the definition of a cluster as kind of the modes in this density field. And want to specifically test for this multi-modality in the clusters. So just to make this specific, we want to have a null hypothesis that states points belong to a single mode, or an alternative hypothesis that says points belong to multiple modes. And we test this modality along paths in the input in the feature space. How this path can look like is, for example, going from one mode to the other, so starting at R0 and going to R1. So this is encoded here on this x-axis. And on the y-axis here, you see the density. So we'll show you multiple of these things. And here we essentially have an alternative hypothesis where we find a density dip when we start from this very dense point. Then we dip, so meaning that the density falls below one of the endpoints. And if we look at a single modal path through the feature space, we have essentially no dip. So how can we formulate this? We write down this test statistic, which essentially takes this H, the null hypothesis, rearranges these terms, and we have added the logarithm here, which will become important later. And then we essentially test if this test statistic is below 0, and if it's above 0, we reject. And we have essentially multiple modes, so this works out quite nicely. So here now we have the test statistic on the y-axis, and if we apply this to now our estimated density, we of course fail. That's the problem in the beginning. However, we have to also plug the density in our estimated test statistic. And if we do this with the KNN density estimator, we essentially take this and move this up in here, and simply moving this up in here results in this t hat, which is a very, very simple expression, and which has been shown in 2009 that this converges in an appropriate way to this original t here, and under the null hypothesis is standard normally distributed up to a constant factor. So if we divide now this constant factor out, we have a normalized test statistic here, and if the value of this test statistic is very high, we can reject the null hypothesis. So let's test this. So again, we have our path now on the real data, and if here we see this dip here in density, and if this line shoots above this threshold, we reject the null hypothesis, meaning we have multiple modes in our dataset. Perfect. Here we see a KNN estimated with 10 nearest neighbors. And if we have our path again in one of these modes, we don't overshoot. Perfect. Seems to be quite robust. You have to trust me that this is also robust for higher dimensions and larger data. And if we now put this all together, we essentially come out with our clustering pipeline, which starts by starting with this gradient ascent step which produces this cluster tree, which overclusters, and then we iterate through. The saddle points from highest to lowest density, and at each saddle point, we ask, is this path from one node over the saddle point, which constitutes this minimum energy path, is this path a single modal path or a multimodal path? And if we cannot reject the null hypothesis, then we merge these two. So if we do this iteratively going through lower and lower saddle points, we end up again with our robust, remerged, pruned cluster tree. And for example, just plugging in some values, this is the clustering result here. Okay, maybe some final thing, how to set these parameters. This actually only is normally distributed for some values, so we can just iterate over these values and essentially build up this kind of scale space and track stable clusters through the scale space, and essentially just keep the stable clusters in this smoothed out family of density estimations. Choosing alpha is also quite natural. So since we have many hypothesis tests along this path, and the chance of finding false positive increases as the number increases, we apply this Benjamini-Hochberg procedure and have with this a data-driven way of choosing our significance threshold. So no parameter tuning required here. Now quickly to the results. So I've showed you this region of space. In there sits this Gaussian OB association, which is the closest OB association to us. And we have a lot of projection effects. We have a huge area on the sky that this association takes in. And using our algorithm, we find this colorful mess consisting out of 37 clusters with unseen substructure before, which we can perfectly validate. And with this, I thank you very much.
Okay, can take 1 or 2 questions. Any? Paris? Well, I will have maybe one. So because it looks like to be related to the persistence theory, I mean persistence in Morse theory, so there any difference that you can highlight?
It's very similar. So I've showed you, I think, one methodology essentially of pruning this is using persistence theory, but you don't really have any hypothesis test behind this. Which is very, very hard then to choose thresholds which you can actually use if you are in the very large data regime. So maybe I can't go back. Yes. Yeah, this paper by Chazal actually is a persistence-based method.
Maybe a question in New York?
Do we have any question? I believe we are fine, Gillen.
Okay.
Okay, thanks.
Then thanks. Thanks to the speaker again.